I will collect that now, but I will not collect it late. So, yeah, you'll have to stable.
Where do we go with this?
To me, is it stapled and everything?
Yes.
Yep. Or clip's fine.
It has a name on there too.
That'll be great. Thank you.
So that we won't be like Riley.
Okay, thank you. He broke it. No go? No. Just run across the hall, room 316 right here. Should have a stapler there. Anybody else turning in the mini exam? Thank you, sir. Oh. All right, we're going to go like another 30 seconds and we're going to start. Okay, thank you. All right, last call. Oh, David, okay. All right, so last class we were talking about vector functions or space curves. We talked about the derivatives of space curves and how that gives you a tangent vector, or actually a new vector function, which gives you a vector that is tangent to your curve at every, I guess, point in time, you could say. And then we did a little bit of, we talked a little bit at the end about how if we start with the position function, that the derivative is the velocity function, and that the magnitude of the derivative is the speed of the particle at a point in time, and that the second derivative would give you the acceleration function. So now we're going to go the other direction, and we are going to talk about the antiderivative of a vector function. So if you're given a vector function r of t, and in this case we're going to go a three-component function, then the integral, so this is the notation, integral from a to b of your vector function, again, good news here. If you're going to integrate a vector function, all you have to do is integrate each component function one at a time. So that's nice, right? We don't have to worry about anything, any sort of weird rules or anything like that. In this case, it's a definite integral, right? So our answer, if we do this definite integral, this should be a number, this should be a number, this should be a number, and all of those together will create a vector, all right? So we'll just do a quick example. So let's find, or evaluate this definite integral for this vector function r of t. So we want to do the integral from 1 to e of r of t dt. So here we go. So to do this, we're going to do three separate integrals. Integral from 1 to e of the first component function, e to the t dt. Then the integral from 1 to e of t root t minus 1 dt. And then integral from 1 to e of natural log t dt. So that's what this is equal to. Now this example is just, let's see what we remember from integration here. This first one's pretty straightforward, right?
Yeah.
So antiderivative e to the t is itself, so we should just get e to the t. And we're not going to have a constant of integration because it's a definite integral, so we're going to be evaluating that at these 2 points, right? So you'll plug in e here and then subtract from that what you get when you plug in 1. The next one, how about the antiderivative of that? We might actually need to look at that one on the side. So let me just put that one over here. I'm actually going to treat it like an indefinite integral right now, so I can just find its antiderivative, and then I'll come back over here and plug it in. So how would you go about that one?
Substitution.
Substitution? What would your substitution be? T minus 1?
Yes.
Yeah. So if u is t minus 1. Now at this point, I think it's going to vary from your experience with integration, how you set things up and how you actually do this. Notation can be slightly different between professor to professor. So the way that I do this, I set this up and then I differentiate with respect to t on both sides. And the derivative of that's just going to be 1 dt. So that's the way I do it. And then I go back in here and I rewrite the integral. And what would I replace t with? U plus 1. So you solve that for t. So u plus 1 here. And then this would become root of u, and then we'll have dt is du. So we've rewritten the integral in terms of u now, but now we can actually work with this because we can pass this through the parentheses. And so we have the antiderivative of u to the 3/2 plus u to the 1/2 du. And those are just power rules, right?
Yes.
Okay, so let's go ahead and we'll just write the antiderivative over here. The antiderivative of this should be u to the 5/2, but out in front of it, 2/5, right? So we'll have 2/5 u to the 5/2, but u is t minus 1. So t minus 1 to the 5/2. And then we have plus antiderivative of this would be 2/3 u, which is t minus 1 to the 3/2. All right, everyone agree with that? Understand what I'm doing there?
Yes.
Okay, and then we have the evaluation bar 1 and e. So we'll have to plug those numbers in. And then the last one?
And it's going to be 1 over t, I believe.
That's the derivative, be
That's
careful,
the-
yeah.
you're right, I had-
The antiderivative of natural log of t. So I know in my Cal 2 class, we go through and we actually figure out what it is, and then I tell them just add this to your formula sheet. Yeah, but we'll do it with t here, right? So t ln t minus t. So if you didn't know that and you didn't have a table to reference, anyone remember how you do that one? What technique of integration you use on that? Integration by parts.
One as the u.
You use the natural log t is the u.
And
The dt, the 1 dt is the other part. So using integration by parts, you should be able to get to t ln t minus t. That's the antiderivative here, and then it's evaluated again at the 2 endpoints and close off your vector. I think I'll stop at this point because all you would have to do is just plug in, plug in, plug in, plug in, plug in, plug in. You get some nasty looking numbers, but you just leave it. Okay, that's you'll have a number here, a number here, a number there. And so that vector is the integral, the definite integral. Questions or anything on that? All right, so here's a slightly different problem. Give you a vector function, 3-dimensional, t e to the t, times t e to the t. And then I'm giving you that's the derivative, right? That's the derivative of a vector function r of t. And then I tell you that r of 0 is 1, 1, 1, and I'm asking for you to give me what the original vector function is. So how are we going to recover r of t from its derivative?
You take the antiderivative.
The antiderivative, right? So we are going to say that r of t will be the antiderivative of r prime of t dt. Now this time I do not have a definite integral. Okay? We're just using the property that the antiderivative of the derivative should give us back the original function. Now we're going to be off by a constant, remember, because this time it's not a definite integral. But let's see how that comes into play. So this is going to be the vector, which is the antiderivative of the first component function, t, with respect to t, then the antiderivative of e to the t with respect to t, and then the antiderivative of t e to the t with respect to t, right? So what would be the antiderivative of t here? 1/2 t squared, right? Plus some constant of integration, right? So I'm going to just call it plus c. But I'm going to have a constant for each of these. So I'm going to call it c1. Right? So I'm going to call this plus c1. And then the next one, the antiderivative of e to the t is itself. But that's going to have its own constant of integration. And then finally, this last one, we would have to do integration by parts to get that one. So unless someone knows what it is, we might need to go through it. So I'm curious how people do integration by parts, because again, there's shortcuts and like these. Have y'all seen that one where you do those little diagonal things? Yeah. There's all these different cute things you can learn with integration by parts. You know, the way that I do it is this is the way I teach it. I set up a table, put u du here and dv and v here, and then I use that formula, ultraviolet minus voodoo. Have you all ever heard that before? No? Ultraviolet minus voodoo? Okay. So this is all Cal 2 stuff, right? I don't need to go through this, but I will. If you're trying to find the antiderivative of u dv, this should be u times v minus the integral of v du. So that is our integration by parts formula. So I heard it, I learned it when I was a student, ultraviolet minus voodoo. I don't know, just that's the way it was taught to me. Now you have to remember the integral sign, but ultraviolet minus voodoo. So here, when I'm at this point, I have to determine from what I'm given what is u and what's dv. So I'm going to pick my u to be t, my dv will be e to the t dt. And once I pick those, then to get du, I go down here, differentiate, and then I integrate to go up here. So I go dt here, that's the derivative of that, and then integrating this, I get e to the t. And then once I have this table filled out, I just go here and do ultraviolet minus the integral of voodoo. So what would ultraviolet be? T to the t minus the integral, and then voodoo, v du, is this part, which is e to the t dt. And fortunately for us, this is something we can integrate. So we're there. We have this minus e to the t e to the t minus e to the t, and then plus a third constant of integration. Yes, I realize you could factor an e to the t out there, but let's just leave it. So this is our original vector function r of t within a constant, kind of, right? It's not a single constant, though. So I would like for you to kind of visualize this way. Man, this rag, I went and washed it out because it was so nasty, but now it's too wet. I want you to look at it this way. We have 1/2 t squared e to the t, and then t e to the t minus t plus C1, C2, C3. Y'all see how this is the same as this? And therefore we have a vector constant of integration, right? It's a constant of integration, but it's a vector. So you could almost look at this as being like the C vector, right? So I do not have the final answer yet. I have not used one piece of information, and that is that when I plug 0 into this answer, right? When I plug 0 into this, it should spit out the vector 1, 1, 1. And if I use that information, I should be able to recover what C1, C2, and C3 are. So let's do that now. And I'll have to use the other one. So R of 0, what would happen if I plug 0 into our answer here? We get, let's see, 0 here. E to the 0 is 1. 0 times that's going to kill it, minus 0. So we get 0 in the last part, right? So that's the first part. Then I have plus C1, C2, C3. That must equal the vector 1, 1, 1. And can you do that just visually? Right? So what's C1? C1 is 1. I'll just put it here. So C1 is going to be 1, C2, 0, and C3, 1. So those are our constants. So if you replace, if we want a final answer, right, then this one would be a 1. This C2 is gone, it's 0. And then that C3 is 1, right there. So this line right here is our R of t. Sorry, I forgot to silence my phone. Any questions? That's really just to show you, it's very similar to stuff that you did in Cal 2. You start with maybe like an acceleration function and then get all the way back to the position. Yes?
The last one, you rewrote t to the t minus e to the t as t to the t minus t.
Oh, I did. Shoot. Y'all see that?
Yeah.
Why didn't y'all say something? This one right here? Don't know why I did that. That changes our answer, doesn't it?
Yes, it does.
Yes, it does, because this should be e to the t. Sorry, I didn't catch that. So when we plug 0 in there, we actually don't get 0 anymore, right? What do we get? We get -1. Sorry, that changes this. That's -1 now. And now, in order to get 1 here, we need C3 to be 2. Okay. Thank you for pointing that out. 2 here. 2 there.
Would that be your RT equation?
That would be it right there. This is our R of t. I knew when I was doing it, something didn't feel right. All right, so if we are given an acceleration function, so a vector function which is the acceleration of a particle at a given point in time, then the antiderivative of that acceleration function would give you the velocity function. And then if you integrate the velocity function, you get the position function. So this is, again, very similar to stuff we saw back in Cal 2. So this one's very similar to what we just did. What do you think? Should we go through this or not? I give you an acceleration function. I tell you something about what's happening at velocity, 0, and position is 0. So we do antiderivative that first time, which gives us our velocity, right? Within a constant. Then we use this information to get those constants. And we take that and we integrate it again. That time we'll have it within constants again. Then we use this information to get those constants. So it's what we just did twice. So I think we're okay? All right. All right, that finishes up 10.7. So that's the homework assignment for it. And we are jumping now, I believe we're ready to jump into the next chapter. Everything's out of order now. Oh wait, 10.8. Oh yeah, no, we're not ready for the next chapter. Arc length and curvature. All right, so I talked about this when we were first discussing last class, the idea of a vector curve or like a vector function in a space curve, that one of the things we will want to be able to do is imagine taking that curve out of three-dimensional space and kind of stretching it out into a straight line and measuring how long that is. So that's what we're going to do here. And here's the formula for it. So first of all, we have to have a vector curve, in this case in two-dimensional space is where we're going to start. And that we have some restriction on t, so we have a definite starting point and ending point for the curve. Then the arc length of the curve is the integral from a to b of the magnitude of the derivative of the vector function with respect to t. So remember, the derivative is easy to take. Its magnitude means square root of the sum of the components squared. So that looks like what we're doing is, maybe I can kind of motivate this with this idea. Go back to Cal 2 for a second. And this may be obvious now, and hopefully as we move through this class, you'll see why it's valuable to look at this. In Cal 2, when you're learning about integration for the first time, how many of you actually had to do like Riemann sums by hand? Anyone have to do Riemann sum by hand? Okay, you know how those are pretty tedious, right? Okay, well, the basic idea is this, that we are taking this, we're trying to find the area underneath this curve, so what we do is we cut it into these rectangles, right? And we calculate the area of one of these, and then we add them all up. And then what we do is we take the limit and we let each rectangle become like infinitesimally thin, right? That's the idea of a Riemann sum. So our formula is that we say, okay, well, this right here, the width of this is like the dx, right? It's like this infinitesimally thin change in x. And the height of this rectangle, how tall it is the function evaluated at some value in here. And then as we narrow it down, the value in here doesn't matter as much. So that's our height. Some evaluation of the function at some value x within that rectangle. And so the area of this, right, the area is just, length times width, or however you want to look at it, is those two multiplied, right? And that's the area of one rectangle. And then what we do is we add them up, and that's what the integral is a type of summation. And then the a and the b just give us where we're going to start and where we're going to stop, right? So that the symbol, these symbols come from the idea of just a geometric picture of a rectangle and its area, right? Have you all made that connection? Okay. So in the formula we just got, if we have a vector function in two-dimensional space, right? Some two-dimensional space curve, and let's say that it looks like this, right? Then this starting point is r of a, this ending point is r of b, and the formula that we're being given is this, that to find the length of this curve, what we're going to do is we're going to take the derivative, take the magnitude, and do this computation, right? So let's see if we can't visualize what this looks like here. Can anyone kind of explain like what this is in this picture, kind of like what it is over there?
It's taking the derivative, taking the length of RT, of the vector RT, and then deriving it. And then that's the antiderivative. It's a derivative of the length of RT, and then you antiderive that and get your answer.
The derivative of r is a vector, right?
Yes.
The derivative of r is a vector, and that runs tangent to the curve at some point in time.
Yes.
So like if I come to some point on this curve and then take the derivative, it's going to give me a vector like that. And depending on where I am, right, that will be, the length of that vector is going to vary possibly, right? But I'm going to take that and I'm going to take its length, which is how long it is, right? Right there. That length is this part. And then what am I going to multiply that by? By a very small infinitesimal unit of t, which is like time, like a clock running almost like in the background, all right? So what we're trying to do is approximate the length of this. So it's like we're trying to approximate this little curve with the length of that arrow times some little infinitesimal unit of time. So imagine if there were actually 2 points here. If there were 2 points on that curve, like let's say here and here, we were trying to estimate this curve. We could estimate it with a straight line, and then we could create this right triangle, right? And shouldn't this be kind of like our change in our x direction, our x component? And this should be our change in our y component. So this is kind of like the change with respect to time of this direction, which is f, right? So this is like f of t, sorry. And then this right here is the change with respect to time of g of t. Make sense? And so this length right here should be Pythagorean. It should be the square root of this square plus this squared, right? Which is this part, right? Do y'all see that or no? You know, this right here. Let's go ahead and take the derivative. If you take the derivative of this, what would you get? F prime of, it would be like f prime of t, like dt, plus, oh, we need to square it. And then the same thing for this one would be like g prime of t dt, then square that. And then what you can do is take the dt squared out of both and bring the dt squared out of the root. And that's where this comes from. I hope that kind of illustrates visually what's happening. It's not so important that we understand it completely visually, but as we proceed on through the course, the more we can visualize, I think the easier it is to kind of accept what we're doing. All right, so let's do an example. We want to be able to find the length of a curve. Well, the answer to this should be what? What should the answer to this be? The circumference of a circle, of the unit circle, right? That's basically r of t there just draws a unit circle. As long as t is between 0 and 2 pi, right? So that just draws a unit circle. We want that arc length. We know it should just be the circumference, which should just be 2 pi r, right? But let's do that. 2 pi times r, but it's a unit circle, so 2 pi should be our answer. So let's just verify it. Let's just verify it. All right. So the length of this will be equal to the integral from 0 to 2 pi of the derivative of that, right, magnitude. Let's go ahead and do that over here. The derivative of this is the vector function negative sine t cosine t. And then the magnitude of this derivative is going to be the square root of that squared plus that squared. Oh, check that out though. Right? That's nice. This is just 1. So this is just 1. So when we come over here, all we're doing is we're integrating 1 dt. And that's pretty clean, isn't it? It's just t, evaluate at these two endpoints, and you get 2 pi. In fact, what would happen if we were trying to use this to prove the circumference formula for a circle? Like if someone said, hey, prove to me that the circumference of a circle is 2 pi r. Then what you could do is you could start this problem over. You could put an r in front of that cosine and an r in front of that sine, right? And that would give you an arbitrary radius. And then when you run through this part, what changes? You just have an r here and an r here, right? And then what happens in here? You'll have r squared there and r squared there. You can factor out the r squared and take that out of the root, and that will leave you with a what here? An r, and then the rest goes to 1. And then when you come over here and do this integration, this is r, and therefore your antiderivative is RT, and everything works out the same, and you get 2 pi r. So I mean, that's just a way you could prove the circumference formula for a circle. All right, in three-dimensional space, what changes? Yeah, nothing really, just you have one more component to worry about, that's it. But in terms of the computation, it's exactly the same. It's the integral, definite integral of the magnitude of the derivative of the vector function r. So it doesn't matter, you're still measuring kind of that length of that tangent vector. So you recognize that one right there? What does that draw? We did talk about that before, kind of. Yeah, it's like a spring, right? It's drawing a circle, but it's moving up. So there's something a little different on this one. Do you all see the difference between this one and the last one? I mean, other than the fact that this is in 3 dimensions, the other one wasn't? We don't have A and B directly given to us. We have the 2 actual endpoints. So what we need to do in setting this up to find this length is we need to figure out what the A and B are. So what A do you plug in? What number do you plug into that vector function to spit out this point? And this is again one of those easy ones where you can tell by just looking at this right here, right? This last coordinate is t. And you can check for yourself. Cosine of 0 would be 1, sine of 0 would be 0. So that would be the first point. What would be the second one? What would be the second, the b for us? Pi, right? Okay, so a little bit hidden, but it's not that hard to get. Now we need the derivative of that. So let's take our derivative over here. So derivative of this would be negative sine t, cosine t, and 1, right? And then the magnitude of this is going to work out very similar to the last one, right? But not exactly, right? It's this squared plus the other one squared. That one squared right there. And that's going to come out to be root 2 instead of just root 1. So this is going to be root 2 dt. You should get root 2 pi. Nothing special here, right? Do you all agree? This is mechanically, it's as long as you can take the derivative and take the square of the sum of the components and do the integral, you're in business. All right, this one looks a little bit nastier. Why don't you try this one? See what kind of integration you run into here. So I'm going to give you some time. I want you to work on this. You're trying to find the length of this arc, or length of this curve on 0, 1. So I'm already giving you AB here, right? All right, I'll leave that to you. I'll continue to let you work it. I'm going to work it on the board here and just see what we're getting here. Oh, wait, hold on, 2/3. Oh, +4, yeah. Why am I? Okay, thank you.
What?
2, yeah, that should be 1/9. Hold on. 1/9. Is everyone kind of good through this if you're following along here? Yeah. I just did this one mentally here from here to here. But you could do just like a basic U substitution here to get to this. And then let me just clean this up. This is 2/27. 9t plus 4. So we'll plug in 1. We get 2/27 times, let's see, 1 goes in there. We get there 13 to the 3/2. And then minus, we plug in 0. So this is like our exact answer. We could get a decimal, but that's it. Yeah.
Meh.
Nothing again too messy there, I don't think. Whoa. All right, moving along. Talk about something called curvature. So curvature is actually an important concept. It will come up later. The curvature of a vector function is a number, right? So it's a number which is going to represent how quickly the curve changes direction at a given point. So it's kind of like if you're moving along this path, you know, you're kind of weaving along. At any point you calculate the curvature, and it's some numerical quantity that it somehow quantifies how sharply you're turning or how quickly you're changing direction. And the way we do it, the way we calculate it is, well, this is the notation. Curvature, we use K for curvature. K is equal to, you recognize capital T? No. Capital T was the unit tangent vector. So I'll remind you here, I'll put the formula up here so you remember. The capital T of T is equal to the is r of t divided by its own length. So if we start out with a vector function and we divide it by its own length, we get the unit tangent vector function. And this wants us to take the length or the magnitude of that derivative of that. So it's almost like we have to take a second derivative, right? So we take that, and then we take its derivative, and then we divide that by the derivative of r of t, and we take the length of both of them separately and divide. That's one formula, all right? You can use this formula to calculate the curvature, or you can use this formula. The only difference between this one and this one, or one of the main differences, this one involves a cross product. And since it involves a cross product, we'll have to be in three-dimensional space, which means if we're in 2D, we have to extend it to 3D to be able to use this. But you can see the computations are very different, right? For this one, you have to get the derivative of capital T of t. Here, you have to just do the first and second derivatives, cross them, then divide by the first derivative cubed. So which formula you use is kind of up to you, but we'll see in the next example that sometimes one formula is better than the other. So let's do an example of this. Should I write those down on the side? I'll just refer back to them if we need them. All right, so here's our first very basic example. We're taking this r of t, is cosine t sine t, which is our unit circle. Any idea of what the curvature of this would be? Like, it's going to be a number, right? Do you think the number is going to change as we move along this curve?
No.
Should be the same, right? Because the circle always has the same curvature to it. So our answer should just be a number, a fixed constant. Let's see if that happens. So let's use the first formula, right? The first formula, right there. Oops, too far. I'll leave it there for now. Let's get capital T over here first. So what is capital T? It's that thing divided by its own length, right? Okay, but what's the length of that? What's the length of that vector function? 1, right? Isn't it? Okay, so we just got kind of lucky here. So capital T of t is the same as r of t. All right, so then what is the derivative of that? Well, that's not too bad either, right? And then what is the length of that? It's also 1, isn't it? Just do these squared and add them together, take the square root. You should also get 1 there. So the numerator is 1. And then the denominator would also be the length of the derivative of that. So if we go back over to here, we take the derivative of this. We get the same thing as over there. We take its length, so we should get 1. So the curvature of the unit circle is 1. And that, I think, makes sense, yeah? Okay. If this were changed, I'm just curious if we think through this. If this were changed to like r, our original function. So now we have a circle of radius r instead of 1. Would that change our curvature? So what would change over here? We would still have r here. We'd still have r here, right? We take derivative. We'd have an r here. We'd have an r here. And then what would the length of this thing be? It would be r, right? It would be r. So the top would be r. And then what about the length of the derivative of that thing over there? So we take derivative of this, and then take the magnitude. It would also be r, wouldn't it? So our curvature would be 1. It's kind of strange. Because, you know, a really big circle is not going to curve as much. Does that seem right to you? Mm-hmm. Or does it curve the same?
It is the same.
Well, in terms of curvature, it's the same. Okay? 1. All All right, let's do another example, one that is not as easy. I feel like I missed one. Hold on. No. Okay, so this was just a visualization to show an example of a vector function that has a non-constant curvature. So I have the computer calculating the curvature for us. And in the very beginning, your curvature is very large. So let me maybe slow this down. Too much. Back it up. So look in the beginning here. Stop. In the beginning, our curvature is what? 423? It's a very tight spiral here in the beginning. Then as we go out, right, the curvature starts to get smaller and smaller and smaller. That's just a visual example of something where the curvature is not constant. All right, let's look at this one. Find the curvature of this. T 1 plus t squared. Should we try the first formula? See what happens? Okay, so what is capital T of t? So we need to take that vector function and we need to divide it by its own length. Its own length is each of those components squared and added together. So I squared that, squared that, squared that, added them all together, and that's where I'm at. But this is equal to, remember this is a scalar, so this scalar goes into each component, doesn't it? So I'll have t over square root of, let's see, how many t squares? I've got t to the fourth here, got 4t squared plus 1, and then the next component is the same thing. And the last one is 1 plus t squared over that same thing. Ugh. What are we supposed to do with that now? So the formula was we needed the derivative of capital T, right? And then take its magnitude. Jeez. So can we appreciate what this would require? Take the derivative of that. So you got like quotient rule or something here. Quotient rule, right? And then we're going to take the square root of that when you're done and square each component. Right? I'm thinking maybe we should look at the other formula. Maybe we should look at the other formula. So the other formula is this one, right? So I need the first derivative of r cross with the second derivative of r, take the magnitude, and then divide it by the derivative of r cubed. So let me put that over here so we have it. Need the derivative of r of t crossed with the second derivative of r of t, find the magnitude of that, divide it by the derivative of r of t, that quantity cubed. So let's see if this one is better. So I'm going to start over, right? And go back, because I don't need capital T at all for this formula. I just need the first and second derivatives, right? So the first derivative of this vector function is nice, right? 1, 1, 2t. And the second derivative of this is even better. 0, 0, 2. Right, there's my first and second derivatives. And when I do the cross product of these, I can do that thing where I do that, right? So let's do the cross product. So cover here, what do we get there? 2, right? Just 2. And then here, 2. And then the last one, 0. Oof, that was really nice. And then I'm going to need its magnitude, right? So I think I'm ready to do this. The curvature is going to be the magnitude of the vector 2, 2, 0 over the magnitude of, what was the first derivative? 1, 1, 2t, that cubed. Okay, the numerator here is the square root of what? Square root of 8 over the bottom is the square root of something, and then it's going to be cubed, right? So 1 squared plus 1 squared, right? It's 2 plus 4t. So you can see here that the curvature is a function of time, or function of t. As t gets larger, the curvature gets smaller, right? As time goes on, this thing gets bigger, this ratio gets smaller.
Would it be 4t squared?
Pardon?
Would it not be 4t squared?
Man, that's 3 today, right? It's 3. These are minor, but they're, I'm still going to get punished in math hell for them. Okay, square that is that, obviously. Yeah, I'll see you there. See you, that'll be fun. All right, y'all good? It feels like Friday, I think, to me right now. All right, I want to go back. We said that the curvature of a circle is constant, regardless of the radius. It just doesn't seem right. Is it? Regardless of the radius?
Yes.
So we have, if r of t was r sine t, r cosine t, that's 2-dimensional, right? I'm going to make it 3-dimensional. And I'm going to try and use the formula we just had, see if we can do it that way. What would the first derivative of this be? So, right, I'm going to use that formula, so that would be r cosine t, negative r sine t, 0. Second derivative of this would be, so we're just going to go again. So this time, what do we get? Negative r sine t, and then negative r cosine t, and then 0. And then we're going to cross. I'm just going to put cross here, so I'm not going to write all that again. So when we cross this, what do we get there? 0. Okay, here, 0. And we know this from our past experience that when we extend into 3 dimensions, we know that these two components will always be 0. We're only going to get something here in this last component. So that one will be, let's see, negative r squared cosine squared t. And then we have minus this, but that's a plus, so minus? Minus r squared sine squared t. And then we could factor out a negative r squared from that. And so this all just becomes just negative r squared, right? So now what we need to do is take the magnitude of that, right? Take the magnitude of that. So what's the magnitude of this vector? So k will be the square root of this squared plus this squared plus this squared, right? So the square root of r to the 4th, so just r squared. So the top is r squared, and the bottom is the derivative, right? Take its magnitude. So what's the derivative here? Take its magnitude. So what's the magnitude of that? Yeah, so square root of r squared cosine squared t plus r squared sine squared t, which would be just r at the end of the day, right? So this is actually coming out to be r what? Cubed, which means it should be 1 over r. 1 over r. So remember earlier we went through it and we said, what if we put an r in front? Looks like nothing would change. Something in that's not right. It should be a function of the radius. Like if you make a circle bigger, you should have less curvature, right? So you would need to go back and do it using the other formula with r in there to see where that mental mistake was. There's somewhere in there an r is going to appear on the bottom. Should we go through it, or you think you want to go through it yourself, or leave it alone? You want to leave it alone? What do y'all want to do?
I'd rather go through it just in case, so I actually know.
Okay, so what's the other formula then? So remember, we're working with this right here, right? So let's try and figure out where, when we just breeze through it verbally, where the mistake was. Capital T of this would be, capital T of this is that divided by its own length, right?
Yes.
So what happens if you take that and divide it by its own length? I think that's the part right there.
Yeah.
Because what's the length of this? What's the length of this vector?
1.
No, not 1 this time. It's r, because remember this is a circle of radius r.
Yes.
So when you divide this by its own length, all you get is sine t cosine